Let's find the Laplace transform of 4s plus 2 over s squared plus 2s plus 10. Now looking at this, it's easy to get daunted by it, but if you look carefully, it looks similar to the one we did on the last example, where we have this denominator that doesn't look like anything we have in our Laplace table, but if we were to complete the square, we would get one that looks like the exponential multiplied by either sine or cosine. So let's try doing that first. Completing the square on the denominator. We have s squared plus 2s plus 10, and the goal is to get s squared plus 2s plus something that will make it a perfect square, and then we have to subtract off that same thing, and then plus 10. So again, the shortcut is to take this coefficient of s, divide by 2, and square it, which gives you 1, and so you add and subtract 1. So this turns into s plus 1 squared plus 9. And in case I didn't mention it, that thing that you get when you divide by 2, that's the value that shows up here. So there's what we get when we complete the square, which means that we're looking for really the Laplace transform of, or the inverse Laplace transform of 4s plus 2 over s plus 1 squared plus 9. So looking back at the Laplace table, what this gives us is we're looking for either sine or cosine with the exponential modifier. So this is like e to the at cosine or e to the at sine. And if you look at those, you should be able to tell that a should be -1 and b should be 3, because both of them have s minus a squared. So s minus -1 gives us s plus 1. S minus a squared plus b squared. So b should be 3. Now, if you look at the numerator, though, this is where things get tricky, because we have 4s plus 2, and the cosine part includes an s on the top, and the sine part does not. So just as a reminder, let me put these over here. So the Laplace transform of this one is s minus a over s minus a squared plus b squared. And then the sine is b over s minus a squared plus b squared. So both of them have the same denominator, but the numerator on the cosine involves an s, and the numerator on the sine does not. So looking at this one where you have 4s plus 2, we've got to figure out how to make that match one or both of these forms. And the conclusion is it's going to take both of them to make it work, because unless the numerator here is conveniently one that matches either the cosine or the sine, it's more likely you're going to need both to make this work. So let's work on the cosine first, because it's harder to get the s to be correct than it is to get just a constant by itself. So we'll start with the harder part, so that the second half will be easier. So in order to make this work, we know that a is -1, so we want the numerator of one of the pieces to be s plus 1. So we want an s plus 1 in the numerator. Now, it's not quite that simple. Because we have a 4s here, we really want to have 4 times s plus 1, or like 4s plus 4. Right? So the reason there is if we pulled the 4 outside of this, what would be inside is what we want to be s plus 1. So really, there's that 4 multiplier that we can't ignore. We need 4s plus 4. So if we're going to make that work, we need to adjust here. So this is going to be the inverse Laplace transform of, we want 4s plus 4. So what we're going to do is we're going to insert in here a plus 4 and a minus 4. to balance each other. So we're not actually changing anything as long as we add and subtract the same piece. So we would get 4s plus 4, and then the minus 4 and the 2 would be minus 2. All right, so if you need to look at that a couple of times to make sense of it, this is where things just get complicated in the details of adjusting these constants as needed. But once we have that, then we can simplify further. So at this point, we can split it up into two pieces. One of these, we're going to take the 4s plus 4 over the denominator, and that's going to give us the cosine piece. And then we can have the 2 over all of this, and that'll give us the sine piece. All right, so splitting this up, we have 4s plus 4 over all of this, minus 2 over all of this. All right, so we're almost done. All we have to do is adjust a little bit more. So on the first one, I'm going to pull out a 4. And what remains is exactly the form of e to the at cosine of bt with a -1 and b 3. So this matches exactly that. So we're close. We're almost done. The second part almost matches the sign, except that the numerator is not right. Now we've done this before. We want the numerator to be a 3, so we're going to multiply by 3 and by 1/3. So let me pull the 2 and the 1/3 out in front, because those are the ones we don't need to make it match the form. But all we've done is taken this 2 multiplied by 3 and 1/3. And then we're done. Both of these match exactly the form of the sine and the cosine. So this is going to be 4 cosine of e to the -t, sorry, got ahead of myself there, e to the -t cosine of 3t. And this would be 2/3 e to the -t sine of 3t. So that's all there is to it. There's a lot of details of moving constants around and completing the square and rearranging things. So it's really just a test of your algebra skills and how comfortable you are doing things like this that you may not have seen for a while, or maybe not in this form. But you're basically just slogging through and finding a way to break these things apart to match the exact forms you need them to match. That's the general structure of one of these problems.